We might be able to do it by the end of the period. I have y'all's. I don't have the other classes. Kind of like to keep in the same place. So if we have time, we'll do it at the end. Okay, so I did get your tests graded, and I believe they're in Schoology. I think I put them in there. That's just a little thing, and I may talk to y'all individually if I think that you're underestimating what you can do in next year or overestimating next year. Just keep in mind, I truly believe that everybody in this class, if you decided you really wanted to take BC, you're not going to fail it. I mean, you'll do okay. The question you have to ask yourself is, where can I put myself in the best position to really understand that calculus and maximize that year? Because some of you, I worry a little bit about if you take BC, your head's just going to be spinning a little bit. And I don't think that you're going to, like I said, it's not a matter of pass or fail if you're coming from this class. You could do it, but getting a C in BC, to me, you're going to leave there with your head kind of spinning. There's a chance you might not even pass that AP test, even if you get a passable sub-score, because they do give you a sub-score on the AB parts. But to me, you want to maximize. You want to walk out of there going, man, I know this calculus backwards and forwards. And if you're making A's on this limits test and the A on this first derivative test, and you typically make A's in this class, I am not worried about you. But if you're making B's or lower on either of those tests, or you typically make B's in this class, there have been plenty of people that have taken that, gone on, made low B's or C's in BC, and that's okay. But I have tons of students who make C's in this class that take a B and they thrive in there. And they make 5s on that test, and they get their confidence back in the class, and they really know calculus super well. In fact, I have plenty of people in my class right now that took my class in 10th grade, and they were struggling in 10th grade, so they went and took regular pre-cal, got their confidence back up, came back into AB, and have thrived in here. I mean, can't give you their names, but I mean, that class is full of people that are thriving and thriving and thriving that may have struggled somewhat in either or both of my math team classes. So if you got an A, I'm truly not talking about you, but that last limits test and this first derivative test, that's an indicator. That's AP Cal stuff, and I'm not even going as fast as Homer's would go. That sucker burns through material. He does. Like, have you ever had those times when you have like 2 or 3 review days in here and some of you are like, I love this. That's AB Cal for you guys, where you learn the material and then you're like, oh, I don't feel so super strong about this. But because we go over it for the next 2 or 3 days, you're like, oh, I'm good now. We've been over it so much. Well, BC is like, oh, I'm not so sure if I get this completely. Too bad test day. I mean, that's kind of how he works. It's just, I'm covering test, cover test. Because he's taking an entire year of calculus and shoving it into 7 months, 7.5 months. Like literally, it's like harder than college because he's taking a whole year's worth of material and packing it into 7.5 months so he can review for the AP test. I'm taking a half a year of material, stretching it out to 7 months, and then reviewing for 2 months. I mean, just consider that, because again, it's not a matter of, I'm not talking to you like, oh, you're going to get destroyed. You probably won't, but do you really want to take Cal 1 and 2 and not feel good about it, and then you go off to college in engineering and you're supposed to now apply that to all these other curriculums? I mean, it really is a course where you're going to use it in calculus and use it in thermodynamics and use it in different other fields. And if you aren't really confident, it can be troublesome. So anyway, just a thought as we're moving forward. We still have another another derivatives test to kind of get a feel for it. This one, most people really improve on this one. And the main reason why they really improve is I'm going to talk about something new today. And that's the last new thing I'm really going to talk about before our test next week. So you're going to get all kinds of time to review it. I'm going to go back over. I did a problem and it was a bonus question for you. Remember the one that you're finding the A and the B value that made the thing differentiable? I'm going to that was just a bonus because I only covered it one time. We're going to cover that again. We're just going to look at we're going to cover some AP trig looking, AP derivative looking problems that you'll kind of get a feel for. We're going to do that on Monday. I actually won't be here Monday, but I'm going to leave you a worksheet. And also, I'm asking you to omit 4 of the problems. If you look on Schoology, I mentioned which 4 to omit. I'm just kind of mentioning that to you. But anyway, let's talk about trig derivatives. Ultimately, you're just going to have to memorize these. Okay, that's it. You're just going to memorize it. And I also want you to understand that what I wrote right here is really kind of missing a part. And I ought to fix that. Did I fix it anywhere else? I kind of really didn't. But let me just mention, this is the actual trig derivative rule, but it doesn't take care of the chain rule. Okay, so let me talk about that. If you ever have, and I'm going to talk about real briefly why these trig derivatives are what they are, because if you're looking at them, you're like, how is a sine a cosine? And then a derivative of cotangent is a negative cosecant squared, and derivative of secant is a secant times a tangent. Makes no sense. It's almost like I'm just making crap up. So I'm going to show you the why, but I'm not going to make you know the proof. Okay, so for those of you that are interested and mildly curious, I'll show you on maybe sine why that derivative is this, and then I'll show you on some other ones using some substitution, and you'll go, oh, fair enough. And I think you'll be at least confident enough to believe that it's true. But after that, you just got to have these memorized. But know this. When you have a function that has a sign in it, okay, the derivative of the actual sine part is cosine of whatever that blah is. But if that blah is anything other than an x, you have to take the derivative of it. That's the chain rule. Are you with me on that? So for instance, if this had been y equals sine of x squared minus 3 instead of just a simple x, you're going to go, well, the derivative of the sine of blah is cosine of the blah, and that takes care of the sine part. But then you have to go back and go times the derivative of the blah, which would be a 2x. And that 2x, don't multiply that 2x by this, right? Because this is cosine of blah times just a 2x. Probably be better to put the 2x in the front, but I don't need you to do that. My keys don't do that right now. Y'all seeing that? And then the derivative of a cosine function is going to be a negative sine of the function. And again, the reason why I don't have anything else here is because that takes care of the cosine. The derivative of a single x is just 1, which is why I haven't mentioned it. But should that have been something like 2x minus 5, you would have had the derivative of the cosine of blah would be negative sine of blah, right? That takes care of the cosine part of the function. And then the chain rule says, now go back and take the derivative of the inner part times the 2. So that's how you would do these trig derivatives if it's a simple trig function. Now they can get much uglier because I can put powers on this. I can put powers on the trig function part. So you can have powers all over the place. I'll show you that in a second. And then you could have a trig function times a trig function. And then you'd have to do a product rule. You could have a trig function over a trig function. You'd have to do a quotient rule. These, you'll see them. These derivatives get really long really quickly, depending on, and I could just, it'll be a little function and you're like, oh crap, it ended up taking me 2 lines to actually do the derivative. So you'll see they can be, but they can be a little confusing at times. But once you get them down, once you understand what's really happening, how the chain rule is being affected, the trig part is just one part of a big chain rule. Kind of like a natural log, there's something you do for the ln, and then you just finish up the problem using a chain rule. Well, there's something you do for each trig function. So the sine of blah is cosine of blah times the derivative of the blah. Cosine of a function is negative sine of that blah times the derivative of the blah. The derivative of a tangent of blah is secant squared of a blah. The derivative of a cotangent is negative cosecant squared of whatever that blah is times the derivative of the blah. And the derivative of the secant is secant tan. The derivative of the cosecant is negative cosecant cotan. Are y'all noticing any patterns on these that might help you remember them? You're staring at all the derivatives. These are a couple little things that might help you remember them when you're memorizing them tonight. What do you notice about the derivative of every trig function that starts with co, like cosine, cotan, cosecant? The derivatives are negative. So if it starts with a co, you know you're going to have a negative on it. If it doesn't, sine, tan, secant, you're not going to have a negative on the derivative. And then have you noticed, if you look at the trig functions like sine, cosine, tangent, cotan, secant, cosecant, look at those pairs and what do you see? Look at those two things. Look at those two things. And look at those two things. If you know the derivative of the sine is cosine, then all you have to do, bless you, for the derivative of the cosine is do the negative co-function of that. So what's the co-function of cosine? Sine, so do the negative sine. If you know the tangent is a secant squared, what is the co-function of a secant squared? Cosecant squared. So do the negative cosecant squared. And if you know the secant's derivative is secant tan, what are the co-functions of those? Cosecant cotan, so negative cosecant cotan. So that might or might not help you memorize, but as you're memorizing these, because you're not going to want to do the proof, you'll see that in a second. But as you're memorizing them, just remember that. And then when you're doing one of these problems, remember you have to consider the chain rule. A lot of you missed that on your test. I gave you a problem, and we had done it the day before yesterday, where I said h of x, and I don't remember what I gave you, whether it was f of g or g of f or whatever. But I gave you something like this. And I said, what is the derivative of h at 1? So you had to find the derivative of h. And a lot of you did first do second plus second do first. And that's what you would do if you were multiplying an f times a g. But are you multiplying an f times a g? No. If you were doing that, you would have seen f of x, g of x. But there's only one x. So in this case, it must have been the g of x was put inside of the other function. That's the chain rule. So if there is a function inside of another function, like a composite function, you've got to do the chain. Now, a number of you also, you recognize that it was the chain rule, but you did this. You just went f prime of blah. And f prime of blah, although it's a great start, you didn't finish, did you? Because that would be like me going, the derivative of sine of x squared minus 5x, that would be like you saying is cosine of x squared minus 5x, and just stopping. You took care of the trig part, but you never did the chain part. What does the chain part say to do? Go back and do what? Now that you've done that, take the derivative of the inside part. Right? So you're going to have those two parts if there's two functions. And if I have a trig function of a part, you got to take care of the trig function of blah, then you got to take care of the derivative of the blah. Are you seeing that? And very quickly, this will go from 2 parts to 4, or 3 or 4, and you'll see that in a moment. But those are the 6. If you force yourself to do the homework throughout this week, you'll know these. Rarely, maybe in a class of 20, I'll have one person who will confuse some of their derivatives. But if you just force yourself to do them, and if you're wise, you'll have your derivatives out to the right, and you'll try not to look at them. I mean, really force yourself to try to do them. Okay, what was that? And if you just can't do it, go look. But try to force yourself to memorize these as you're working. We're going to do so many between now and whenever your next test is next week. You'll have them down, even though it may look like a lot of gibberish right here. All right, so let's check this out. I want to show you the why. So if right now, if you're like, I could care less about the why, my brain doesn't care, I don't care if that's the case, just la, 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 me for the next few minutes. But I wanted to kind of show you the why using our actual definition of a derivative that we learned. And it will only take a second. And again, as long as you can look at this and go, oh, that makes sense, then my goal has been achieved. My goal is not for you to actually be able to stand up here and do this yourself. So here's my proof for why, if you have a function that's sine x, the derivative would be cosine x. So you know the definition of a derivative is, and I'll write it out here, the definition of a derivative of a function f of x is the limit, well, I think you know this, as h goes to 0 of f of x plus h minus f of x, all of it over h. That's your definition of a derivative, right? And we talked about that at the very first day. So if my function is sine, then to do f of x plus h, I'm going to do sine of x plus h. And to f of x, I'm going to do sine of x I'm going to put it over h and take the limit as I go to 0. Now, when I write that out, clearly, if I plug a 0 in, you don't want to sleep through the day, man.
No.
All right. If I plug a 0 in, clearly what happens? Come on. What happens? I get 0 over 0, don't I? If I plug a 0 in for h, sine x minus sine x is 0 over 0. So you know there's a hole. So you know there's a value, right? That you know I can get something. I just have to find a way to cancel out enough junk so that I actually get an answer. Now you could use L'Hopital's rule, except for one thing. To do L'Hopital's rule, what would you need to know? How to take a derivative, and that's what we're trying to prove. So we can't really take a derivative of sine when we're trying to prove sine. So I'm going to have to be forced to be creative. So what I did is I took this sine of x, and you would do this same process with all the 6 trig functions, except it would be a little uglier with some of the other ones, like tangent and secant, stuff like that. So sine of x plus h, we learned that's a sine of alpha plus beta. So if I can replace sine of alpha plus beta with its definition, sine x, cosine x, sine h, cosine x, I'm going to take that and replace that with it just to give me something else to work with. And then I decided I would throw away the parentheses since they're not really doing anything. And then I'm going to put this negative sine x here and this positive thing here. I'm just basically going to change the order. And when I change the order, I'm going to regroup this part with that part. And that's what I've done right here. Okay, and you'll see why in a second. Now, I'm going to look at that part I grouped, and because it has a sine x in it, I'm going to factor out the sine x to right here. And then here's what gets a little interesting, and it bothers some people, but try to work with me. Okay, so here I am right here. Now at this point, I'm still looking at it. If I plug a 0 in, I'm still getting 0 over 0. So I took this and I thought, well, you know what? There's a plus right here. So I'm going to take this first part that I'm circling over h, and then the second part that I'm circling over h, and break it up into 2 parts so I have 2 limits. And I'm allowed to do that. That's a limit rule. I can break it up into 2 limits. Now, I don't know if you caught this yesterday. Do you remember when I told you when you're doing L'Hopital's rule, right? When you're working with a function and you're doing L'Hopital's rule, what's the variable? I said, when you're taking a derivative, I said, there's a variable and there might be other letters in there, but they stand for constants and you have to treat them like constants. Whatever's under the limit. So the h is the variable, which means the x stands for a constant, which means what is this? That's just a number. That's just a constant. And if it's a constant, I can completely ignore it when I'm treating this limit, right? I can even factor it out to the outside. So let's look at this. And then, by the way, so is that cosine of x a constant. So this is a constant right here. And so is that a constant. So let me ask you a question then. What is the limit of this? And you might remember it from your trig rules. What is the limit? I know I had it written on your trig sheet with an x and an x and an x. But what is the limit of cosine x minus 1 over x? 0. So if all of this goes to 0, I have 0 times sine of x, which means all that goes away. Now, if that's a constant, then basically I'm taking the limit of this and then just multiplying it by that constant when I'm done. What's the limit of sine h over h? What do you do when you have a sine of something over something and you're getting 0 over 0? You use the coefficients, right? So right here, I could take that 1 and that 1. You remember that rule for trig? And that gives me that limit is 1 times the cosine of x. Well, all I have left then is the cosine of x. So your limit gave you that. Well, that tells me now that the derivative of sine is cosine. Okay? Now that's with the basic old x. That doesn't bring into the chain rule. That's just really basic stuff. Now I could do this almost exact same proof with cosine. I'm just not going to waste your time. But if I did, you would say, oh, the derivative of cosine ended up being a negative sine. And you would see that based on this rule. Now after that, the derivatives become a little ugly because, you know, your tangent of alpha plus beta is a little uglier. It's that fraction. We didn't even do stuff for cotangent, secant, and cosecant. of alpha plus beta. We just borrow the other one. So you would be doing reciprocals. The math gets really nasty on those. So how about we take another alternate approach? If the sine and cosine work this way, you can, once you've proved them, you can use them. So let's use them, and I'll show you how to prove tangent. And then once I do that, I'd like to believe that you're going to feel okay. So we already, actually, I'm proving secant right here. So here's an example of why secant is secant tangent when you take the derivative. So if I was trying to prove this, now that I've already proven the derivative of sine is cosine and the derivative of cosine is negative sine, technically I didn't prove the latter, but assume it was similar. If I've already proven those two, I could use those proofs for the other ones. So check it out. If I wanted to find the derivative of secant, I could just change it into a cosine. And now to find the derivative, I could just do a quotient rule. So the derivative is low d high minus high d low. And what's the derivative of cosine? Negative sine over the low squared. All that goes away. The two negatives cancel, and I get sine over cosine squared. Well, sine over cosine squared is the same thing as sine over a cosine times a cosine. And what is that? Which, by the way, you could say the derivative is sine over cosine squared of x. You could say that, but they're trying to give you a little bit better ones to use that are all in the numerator. So check it out. If I take one of the cosines and put it below a sine, what do I get? A tangent. And if there's one cosine left on the bottom, what is a 1 over a cosine the same as? A secant. And that's why the derivative of secant is a secant tangent, or a tangent secant. Y'all with me? But keeping in mind, this is if the x is a basic x. So if x is anything other than a single variable, once you're done, you would have to go times the derivative of whatever the x part was, whatever that blah is. Y'all with me? Okay, so with that in mind, hopefully you are. I'm just going to run you through some practice, and that really is all the new stuff. So from here to the next test day, you just have to get more adept at doing these without making little errors, get more comfortable. Mistakes you might have made on the previous test, figure those out, kind of see maybe what you did wrong, make sure you don't do those again. And usually the second test grades are even better. I mean, significantly better. They're usually in the mid-90s as a class. We'll see what happens, but let's take a look. So again, these are just the same trig rules again, but they're in a different order. So see if you remember them without looking. What's the derivative of a tangent? Anybody remember?
Secant squared x.
Secant squared x. You can do these without looking, your money already. And again, that would be the trig part. Then you'd go back and go times the derivative of the blah, but in this case is 1. What's the derivative of the sine? Is cosine of x. And again, some of you are just writing the derivative, but you're not writing f prime of x equals. Make sure you're in the habit of labeling it every time. That's a big deal for AP. Okay? What is the derivative of cosecant? Negative cosecant x cotangent x. Right? And what's the derivative of cotangent? It's a cos, so you know there's a negative. And if you got number 1 right, if you remember the derivative of a tangent is secant squared, then the derivative of the cotangent is cosecant squared with a negative. Because they're going to be co-functions of each other. And the derivative of a cosine, you know with co, it's going to start with the negative. Right? If the derivative of the sine is a cosine, the derivative of the cosine is the co-function of cosine, which is back to sine. And then finally, the derivative of a secant is secant x tangent x. And if you have those down already, you're in great shape. If you don't, no worries. Just keep plugging away at them. You've got a few days, but you'll get lots of practice. Really try to learn them as you're doing them, and don't just rely on your sheet, though. All right, now, here's me trying to make sure you understand the chain rule better. And this is as ugly as the chain rule gets. Okay? Now, walk with me through a little progression here, and then we'll talk about what's in this box. Okay, here's the most basic trig function I could ask you. Something like sine of some blah. Okay, might be an x, might be a 2x, might be a 3x squared, right? But there's some function in here. Are you with me? Now, it's possible that this blah right here actually has a power on it. Now, when you look at that, this is a composite function. There are literally three functions involved here. There's the sine function, there's the squared function, and then there's the blah on the inside. So there's three things that you have to do, one times the other times the other. It's a big linked chain. What do you think comes first? And what is the outermost function here? It'd have to be the sine, because I'm sining this thing squared. This right here is not the same as sine of blah parentheses squared. Do you see the difference? In fact, you shouldn't see this. This means I've got sine of blah twice. Where should I have put that to? Right there. We'll talk about that next. So when you see a 2 on the parentheses, know that it's just with the parentheses. So for me to do a derivative here, I would have to start, we're not doing that yet, I would start by looking at the sine, and I would say, well, the derivative of sine is cosine of blah squared. And what does that take care of? The sine part. And then the chain rule says link it. Some of you linked it with pluses, not many. Remember, don't use plus. And some of you didn't do plus all the time. You did plus randomly. Remember, if it's a chain rule, multiply. Then what do you look at? Now you're done with that. So what part is the outermost function now? The power. So you deal with the power. So 2 blah to the first, but you don't really need to put the 1. And that takes care of the 2. Then what do? You could take the derivative of the blah. So d blah, whatever that would be. Are you with me on that? Do what?
The Beatles song.
It says d blah.
Oh, Oakley D. Oakley.
Oh.
Ah,
Close, yeah.
Come on, forget it.
You're good, man. Are y'all seeing this? Now, to make matters worse, it might not be sine of blah squared. It might be, and that's what I'm trying to show you in the box here, trig function to a power, then to a parentheses to a power. Now, I don't know who created math. I don't. A series of hundreds, thousands of people, probably over thousands of years. But when it really got formalized, at least in terms of parentheses, things like that, I don't know who decided to put numbers right there on a trig function. It makes everybody's life when they're younger miserable. Now, once you navigate that and get accustomed to it, but it's kind of like, it's like people saying, well, I hate coffee. Well, you just need to drink it a lot. Just keep drinking it. You'll grow to like it. Like, why should you have to do that? It might be true, but why should you have to fight through something that's terrible to then just develop an enjoyable addiction, right? So with this math, sometimes it's like, I'm going to rewrite this, so look up here. That A right there is the same thing as me having a big parentheses around the whole thing and having the A there. So what that means to you is, what is the outermost function? It's the A, even though it kind of seems like it might be the trig function, which means when you begin this derivative, you're working on the outermost function. You're doing a power rule first. You're literally going to go A, copy all of that junk down to the A minus 1 power. That's going to be your first step, except you're not going to put the A out front and the A minus 1 there. You have to do it with good form. So when you're doing it, you're going to take that A and put the A out front of the trig, and then you're going to decrease the A and put it right back where it was. So you're going to have A out front, decrease the A by 1, and then there's your blah. And it is a little annoying, but you have to force yourself to learn and write it that way to have good math form. And when you do that, what will you have just taken the derivative of? With respect to what? What part of the function? The power, which means you haven't even gotten to the trig rule yet. Are y'all seeing that? So that first step, when I go a trig u to the b to the a minus 1, and I put the a there and the a minus 1 there, I'm doing the first part. I have taken care of the a part. I don't have to look at it again, but I haven't even gotten to the trig function yet. Now I take the derivative of the trig function. So whatever the derivative of the trig function is, do that. Derivative of the trig function. That's not a 1. That was me just, I could have said d dx trig, but it's early. So I just put trig prime to show you like f prime. And then you just do that and copy down the u to the b part. And that takes care of that. And then you're to the final part where you have something to a power perhaps. And then you go, all right, b blah to the b minus 1. And that takes care of that. And then you finally get to the blah on the very inside and you take the derivative of that. But it's going to be 4 steps many times. So here's an example of one. Check it out. Sine to the 4th of something to the 7th. What's the first thing you attack on this? See, people mess this up because they look at it and they go, well, 7's the outermost function. But it's not, is it? That 5x cubed minus 4x squared to the 7th is inside the sine function. And technically, what is this 4 doing? That 4 is like a power on the very outside. But you can't rewrite it that way. Force yourself not to. So what you would really do if I had written like this is you would have gone 4 blah 3. But we don't write 4 blah 3. We don't do that when we're doing this, do we? So what we have to do is discipline ourselves to go, okay, I am working on this 4. So 4 out front. And then you're going to copy all that down. All of that gets copied down. But you went 4 blah, and then the 3 goes right back where the 4 was. And that takes care of the power of the trig function. But you haven't even gotten to the trig function yet, it's derivative. Then you go to the derivative of the trig function. And by the way, if it's not there, then you don't have to worry about that. Just start with the trig function. But if it is there, deal with that. Then you go to the derivative of the trig function, which you just learned was cosine of blah. That's your second part. And that takes care of the trig function. And then now you're almost home free. You got a power, 7 blah 6. Takes care of the 7. And finally, the derivative of that. And you're going to have to go through those 4 parts systematically. But it's important that you recognize the first thing. It's the order is important, okay? You've got to do that part first, that part second, that third, and that fourth. And if any one of those parts are missing, you just skip it and move on to the next one. You with me? If you get that down, that's as hard as AP is going to make it. I mean, I make my problems, I make them a much less difficult than I used to do before I taught calculus. But now that I teach calculus, I realized I was wasting people's time trying to challenge their ability to do excruciatingly painful derivatives that take them 6 lines to write out. So I don't do that much anymore, maybe a couple bonus problems or something. But anyway, so let's check out a couple of these. If you can do them, I think you'll be in good shape. So we'll start with number 7. Help me out. So if y is that, the derivative of y would be, first step, 3 sine squared of 8x squared minus 2x plus 1 to the 5th. First step, all I'm dealing with is a 3. Everything else would be considered a blah. And you can't forget, don't just put 3 sine 2 times, because you never copied all the blah down. The blah is the other 3 parts. 3 sine 2, the blah is the sine of 8x squared minus 2x plus 1 to the 5th. Are y'all seeing that? All right, now that the 3's done, what do you move on to? Trig function. So the derivative of the sine is cosine. So I'm going to go times cosine of whatever's left there. Well, now whatever's left is just that part that I'm circling. So 8x squared minus 2x plus 1 to the 5th. And that takes care of the trig part of the chain rule. And now you're almost home free, right? You're down to parentheses to the 5th. So what do? Times 5, 8x squared minus 2x plus 1 to the 4th. That takes care of the 5 times 16x minus 2. And that takes care of the very inner part of the blah. So the blah is changing as you go. First part is the power on the trig. Second part's the trig. Third part's the other power. Finally, the stuff on the inside. Try it again with number 8. What do you got? Derivative. What are you going to start with?
6 cosine.
6 cosine, 5, all that other junk. So you just took care of what? The 6. That was the outermost part. That meant that all the rest of that I'm circling, all of that was your blah. And you can see your blah right there on your first step. Okay? So now that you've done that, the 6 is gone. You don't have to worry about it anymore. Don't let it show up anymore. You move on. What's next? Okay, now let me show you bad form. Okay, and a lot of you will do it. Your calculator even allows it, but it's bad form. Okay, people do this. They go times, and they go negative sine of 4x cubed minus 3x squared to the 12th. So what do you think's wrong with that? Yeah, I am not supposed to have two functions back to back like that. You don't write plus a minus. You don't write minus a plus. You don't. If you're ever going to add a negative, we do this, don't we? Like if you go 6 plus a negative 3, you don't ever go plus a minus. You don't. You don't go times a negative. So if you have a negative, what are you going to need to do? Put a parentheses. I usually put a parentheses around the whole thing because it helps me see what part I'm doing. But technically, you can put a -1 in there and just put parentheses around a -1. But again, since I like to kind of see the parts that I'm working with, all right, I like to see, all right, that's the first power. There's the trig function. I just put the parentheses around the whole thing. And that's how my keys will look. If you forget that, I'm not going to even dot you. I'll take off a half of a point. And if you did it 20 times, I'm not going to take off a half a point 20 times. I usually cap it at like 3 points or something like that. But it's a form issue. We want to have good math etiquette. So even though you can actually do that on your calculator, you can go 5 times a -3 and it will do it. It's bad form in math. So that takes care of what in your chain rule? The trig part. And then at this point, you should be home free. This should look like a problem we did. 12, 4x cubed minus 3x squared to the 11th. That takes care of the 12. And then finally, 12x squared minus 6x. And that takes care of that stuff in parentheses. But you can see all 4 parts to this. Right? Okay, in the interest of time, I'm going to jump to number 10. What do I got? 6 minutes? I'll jump to number 10, and we go back to number 9 if we need to. The reason I want to do this is because it has a trig definition that has 2 parts. And I want to show you what people do badly with this. So what do we do first when I'm dealing with this function? I deal with the what? The power, right? Now you'll notice there's no power at the end here, so that's going to eliminate a bit of a step at the end. But power there is always the first thing we attack. So my derivative, dy dx or y prime is 4 cosecant of blah, and then I put the 3 back where the 4 was. And that is taking care of the 4. Now here's the part that people tend to do badly. Okay? What is the derivative of a cosecant of something? It is a negative cosecant cotangent, right? Now if you really what it is, it's negative cosecant x cotangent x, which means negative cosecant blah cotangent blah. So your blah has to go in twice. Don't do this. I see people all the time that go negative cosecant cotangent and write the blah once. We don't do that. The blah has to go in on both. If you go back and look at your rule, you'll see x occurs twice. Well, that means your blah occurs twice. So I have to have cosecant of blah cotangent of blah in the parentheses. So I end up having double parentheses at the very end because I got to enclose that negative as well. Are y'all seeing what I'm doing there? make sure that this thing shows up in both parts because cosecant and secant have two parts. The rest of them, you don't have to worry about that because they only have one trig function. But be careful on this. Make sure you do it twice. Y'all seeing that? And then once you do that, you're home free, right? So all I have is this. Now, you're not going to write the chain rule twice at the end. It's just one part left. So you're going to go times 14x to the 6 minus 15x squared. And that takes care of that. So in this case, 1, 2, 3 parts. You with me? Want to look them over tomorrow when you have more time? You wouldn't have much time today. Let's jump back at number 9 then. We'll do number 9 a little bit below. Here's number 9. So help me out here. First thing you're going to look at. The what? You can look at the tangent first. Why? Because there's no power on the tangent. And it would make no sense to go 1 tan 0, right? So since there's no power, we don't worry about that. So all we're going to do is say, all right, let's just jump to the tangent part. What's the derivative of tangent of blah? Secant squared of the blah. So copy down the blah. And then we get to what? The power on the outside. So 7 blah to the 6 takes care of the 7. And then finally, you with me? Trig part, power part, inside parentheses part. I really hope as you're doing these, or maybe right now you're thinking, well, really, this is just a lesson in the chain rule more than anything. This is a lesson in the chain rule that has just 6 facts that you have to remember, about how to do individual trig functions. And then the order in which you progress through these things is important too. But if you can see this, I think you'll be in really good shape on your homework. Just to give a glance at your homework and let me show you what I'm doing to you. What do you think you're going to do on number 9 here? On the homework, if you just glance up here, let me erase it so you can see. What do you have going on number 9? A product rule. So first, take the derivative of the sine. Plus second, take the derivative of the cosine. All right, number 10, quotient rule. You got product and quotient on 15 and 16. Look at 18. What do you got going on? Is 18 a product rule? No. What would make it a product rule? 18. If that was cosine x, e to the x, product rule. This is cosine of e to the x. So just another chain. Hopefully you're seeing these. Problems like number 21 can get a little ugly, but do the best you can on these, and I think you'll be in good shape. If you have any issues, please come see me in the morning. Just drop in here early, or make sure you ask me before we get into other stuff tomorrow. All right?
What about you?